Okay, hi everyone. So welcome to the talk. So it's my great pleasure to introduce to you Florian Tramèr. So he is currently an assistant professor at ETH Zurich. So he has worked on a lot of things regarding, say, adversarial robustness and also differential privacy. So I think if you have read papers on this, then you probably recognize his name and also his great contribution to this field. So yeah, without further ado, so let's give it away, Florian.
Yeah, thanks a lot for the introduction. And thanks everyone for coming. What I'll be talking about today is really on the side of sort of empirical assessment of privacy in machine learning. So both from an attack and defense perspective, and sort of going to cover a bunch of work, mainly from the past year while I was a visiting researcher at Google before I joined ETH Zurich. So the setup for today is, well, kind of a very general training setup we'll consider for machine learning. We'll think about neural networks here, but everything we'll talk about this kind of applies sort of generally mainly for supervised machine learning. So where you might collect a bunch of data from users and sort of train a model, usually to minimize some form of loss. And then once the model is trained, it gets deployed and can sort of answer questions or make predictions about user data. And we'll assume here, which is very often going to be the case, that the training set has some kind of privacy properties that we'd like to preserve. So maybe the data comes from individual users, and so we'd like for this training and using the final model to not infringe on users' privacy. The problem with this is that machine learning models, once they're trained, can actually leak a lot of information about the training set. So these are just a few examples from the literature from the past few years. So for example, on the top left here, this was a couple of years ago, some researchers at Google had realized that, actually, no, this wasn't actually people at Google. I realized this, sorry, this was, I think, a journalist at some point that just noticed this, that you could tell Google Translate to translate some gibberish from Somali into English, and the translation model would just spit out a memorized biblical verse. So presumably verses from the Bible were part of the training set here somewhere. So this isn't particularly concerning from a privacy perspective, but then the same thing can actually happen with data that is a bit more sensitive. So the image here on the right, this is from one of our papers from 2 years ago, where we looked at memorization in OpenAI's GPT-2 model, and we found that if you prompted this model in a special way, the model would just sort of start generating text, which actually corresponded to the entire contact information of a specific individual that had posted their contact information online. And these issues are not sort of, they're not limited to text models either. So actually, originally, people had studied these kind of privacy issues with image generation models or just image classification models as well. This image here on the bottom left, this is from one of the early papers on model inversion, where researchers showed that if you had a facial recognition model, you could sort of extract an image that sort of resembles one of the identities that the model had been trained on. And so these are sort of some of the forms of privacy leakage that we might want to avoid when training a model. So here what we'll be talking about first is actually sort of going to be the main thread throughout this talk, is we're going to think about privacy from the perspective of a special type of attack that we call a membership inference attack. And this is really, in a sense, sort of the simplest possible privacy attack you can think of, where the adversary is given a trained model and some input, here this image of a cat, and the question that the adversary would like to answer is simply whether this input was in the training set or not. So sort of try to learn one bit of information, the membership of this specific input in the training set. And so this is a very simple attack that leaks only a single bit of information. And we can sort of wonder why it's interesting to study this attack. So people have sort of thought about membership, or sort of about why membership inference attacks are interesting from different angles. On the one hand, you could think of this as an actual attack, sort of leaking this one bit of information about membership can be quite devastating for privacy in settings where maybe your model is trained on very, very sensitive data, maybe medical data that's tied to, say, a specific disease. And so they are just inferring that someone's data was in the training set might sort of let you infer something interesting and something privacy worthy about the user. The other reason you might care about membership inference is because you can use it as sort of a component of other attacks. So for example, in the attack that I showed in the previous slide where we extracted data from GPT-2, in the attack, we actually internally sort of use membership inference as an attack component to sort of filter out text that's more likely to have been memorized by the model to sort of just make the attack more precise. And finally, and this is maybe the main reason why people have been studying membership inference, is that because it's kind of the simplest form of privacy attack, you can use it as a sort of upper bound on how much a model might leak, in the sense that if you can show that membership inference is not possible, if like an adversary cannot even infer membership of training examples, then in some sense you're good. Probably the adversary will not be able to like extract data or do anything bad either. So in that sense, you can sort of think of as an analogy maybe to people who know a bit about the formal theory of cryptography. I like to think of a membership inference attack as kind of being the analogy for data privacy of something like a chosen plaintext attack when we talk about secure encryption. So sort of a very formal and simple attack model that's kind of interesting to study, and both for attacks and for defenses. And so today we'll be talking about membership inference first in terms of how these attacks have been evaluated in the past. And the argument I'll be making here is that these evaluations have been somewhat flawed, and that we kind of propose a better way to evaluate whether a membership inference attack is successful or not. And by doing this sort of better evaluation, we also find that actually pretty much all prior attacks in this space don't really work. And so we propose a better attack that actually succeeds in inferring membership. And as we'll see a bit later in the talk, this attack works particularly well for data outliers. And it actually only works for data outliers. And then we'll talk about a stronger attack that we came up with a bit more recently that actually works for any input, to infer membership of any input. And then at the very end, I'll conclude by talking about some simple attempts at defending against membership inference, some which will work and some which won't work. So let's first start by talking about membership inference and how these types of attacks should be evaluated. So to give a bit of a gist of how membership inference, sort of old school membership inference attacks work, these all start from sort of this basic premise that the way we train a model is to minimize some kind of loss. It doesn't really matter what the loss is. You can think of this as like cross entropy loss in general. And so what this means is that we are slightly going to overfit onto the training data usually. And so the model's loss on the training set is going to be on average sort of slightly higher for training examples than for test examples. And you can visualize this as follows. So if you look at the members of the training set and the non-members, and you sort of plot the loss that you get for all of these examples, you'll get sort of some distribution that might look something like this. And from here, sort of what prior attacks have done is to sort of look at this and to say, well, we can just take a threshold on the model's loss and sort of say, well, if the loss is smaller than some threshold, we'll just guess that we're looking at a member, and if it's higher than some threshold, we'll guess that it's not a member. And you can sort of set the threshold kind of wherever you want. This might sort of give you slightly higher precision or higher recall. But you can already see a bit from this picture that this might just not work particularly well, because there isn't actually a threshold that really nicely separates these distributions. And so when you then want to evaluate the attack success rate, because you can sort of set the threshold in many different ways, what's sort of quite common in the field is to look at what's called a ROC curve, so where you plot the attack's true positive rate, so sort of its ability to actually infer membership, at a fixed false positive rate, which is kind of the rate at which your attack guesses that something is a member when it's not. So the amount of mistakes that your attack makes. And then you can sort of, for every threshold that you pick, you sort of get a different trade-off between true positive rate and false positive rate. And you can then sort of plot this like this on a curve. And what also many papers then report to sort of have a single value to compare different attacks is the AUC score, which is the area under the curve, which is sort of just a kind of an average of this trade-off between true positive rate and false positive rate. And the problem that we claim that the problem with this approach is that this essentially amounts to sort of measuring the amount of information that the model leaks on average across the entire training set, across all the points. And average case leakage is a very poor metric for privacy because it doesn't really tell you anything about your privacy as an individual. If this attack has a certain AUC score, it really doesn't tell you whether your data is vulnerable or not. It just sort of tells you that on average across the entire training set, the model is sort of making slightly different decisions on the training set than on the test set. And so it's kind of hard to reconcile this with an actual privacy threat. So instead, what we suggest is that we should be evaluating how well these attack works at low false positive rates, which is essentially means in a regime where you know that the attack makes where the attack makes very few mistakes. So you're very rarely claiming that something is a member when it's not, and so you actually have an attack that's extremely precise and can really sort of say this specific point is a member with very high precision. And so this starts becoming much more of a privacy threat. And the issue is that existing attacks, when you sort of look at this low false positive rate regime, they actually do no better than random guessing. A better way to visualize this is actually if you plot the ROC curve in a log-log scale. So here it's the same thing as before, just we've switched the axes here to be on a log scale. And so here we see that as soon as we sort of think about low false positive rates, the attack really does no better than random guessing. If you want an attack that sort of only incorrectly guesses membership, say 1% of the time, it's essentially going to be equivalent to an attack that just randomly flips sort of a coin and decides like 1% of the time that it's gonna guess that something is a member. And so if you view existing attacks this way, they're not an attack. It's essentially you're not inferring anything, you're not leaking any information, you're essentially just doing random guessing. It turns out that actually, if you look at prior attacks in the literature, not every attack does quite as badly as this sort of uniform thresholding attack that we've looked at so far. There are actually attacks that people have proposed in the past that do much better at this low false positive, in this low false positive regime. So for example, there's this attack from a very nice paper from Sablerol and his co-authors from a few years ago, sort of at low false positive rates does sort of 100 times better than this uniform thresholding attack we saw before. The problem is when Sablerol and his co-authors proposed this attack, they didn't actually realize that this was the case because they and sort of everyone else at the time was they were only evaluating and sort of comparing attacks on sort of average case scores. So in this case, the accuracy of the attack. And if you just look at that's sort of how well the attack works just on average, this attack actually does worse than the uniform thresholding attack. So you might, if you just look at how well these attacks sort of work on average, you would sort of reach the incorrect conclusion that this new attack from Sablerol is actually worse than the sort of simple uniform thresholding attack. But if you actually look at sort of whether either attack is capable of inferring membership sort of confidently of at least some examples in the training set, it turns out that one attack does succeed and the other one just does random guessing. And so this is really why we recommend that sort of future work on membership inference attacks should really look at how well these attacks work in the low false positive regime, because this is really what matters and what sort of shows whether an attack can confidently infer membership for some examples, for sort of some worst case examples, or whether it's just sort of measuring some average case overfitting of the model. So now we're going to see a little bit how we go about developing an attack, a stronger membership inference attack that actually works well at low false positive rates, and sort of getting an attack that works much better than this uniform thresholding strategy we saw before. So really the core insight here is that uniform thresholding is a bad way of inferring membership, because not all training examples or not all examples from the distribution are equally hard to learn. So here, let me give you an illustrative example. Suppose I give you these two examples here, these two images. I give you this cat, and I tell you the model that I've trained has like 90% confidence that this is a cat. This is sort of a very canonical image of a cat. And then I give you this other image, which is like a very blurry and slightly out of distribution image of a truck. And here the model is still very, very confident. It's like 85% confident that this is a truck. If I now ask you to guess which of these two images is more likely to have been in the training set, I argue that you should actually be saying that the right image, the one of the truck, is the one that's more likely to have been in the training set, even though the model's confidence is slightly lower on this image. The reason is that if you look at sort of any classifier that's been trained on images of cats, any classifier is going to have a very high confidence in this leftmost image, because it's a very typical inlier. You don't have to have seen this exact image to know this is a cat. Whereas this image here on the right, which is much more of an outlier and sort of out of distribution example, here a classifier, a model that has not been trained on this specific image is very likely to just get this image wrong, or to have very, very low confidence. And it's only if you see this image during training that the model will sort of overfit, but in a very local sense, to just this specific image, and assign it a much higher loss. A much lower loss. So what this means is if you now sort of try to pick a threshold on the loss to sort of determine what you're looking at, whether you're looking at a model that was trained on this particular image or not, there's not going to be a single threshold that is optimal for all inputs, for all images. For some images that are very, very easy to learn, sort of in distribution, it might just be very, very hard to determine whether they were in the data set, in the training set or not. And then there's going to be other examples like this truck here that are really outliers, where there is actually a threshold you can find that nicely separates models that were trained on this input from models that were not trained. And so here it's going to be possible to do membership inference very well. So this brings us to the attack we suggest, which is called LIRA, for a likelihood ratio attack. So at a very high level, what this attack does is literally just what we saw on the previous slide, is that we take a trained model, we query the model and we calculate the model's loss on this input. And at the very end, what the attack wants to output is this likelihood ratio test, which is just a ratio between two probabilities. The probability that we would have seen this particular loss if we had trained on this input, and the probability that we would have seen this particular loss value if the image that we're looking at had not been in the training set. And this likelihood ratio test is the optimal statistic for a membership inference attack. There's sort of statistical theory that says that if you're trying to infer membership, this is the statistic you should be computing. And this is sort of going to give you the strongest attack. Or actually more formally, it's going to give you the attack with the highest true positive rate for a fixed false positive rate, which is exactly what we want. So now the question is, how do we compute this likelihood ratio? Because these probabilities are sort of very hard to estimate, right? It's sort of like asking us what's the probability over an entire training run of sort of getting a model that spits out a certain loss, whether an example was in the training set or not. So this is kind of a very hard probability to compute. And so we essentially have a bunch of techniques and tricks to approximate these probabilities. The first thing we do is that we train a number of so-called shadow models, which are essentially just models that will try to mimic models that were either trained with or without this specific example we're trying to target. So what we do here is we just sample a training set from the distribution we care about, and either include or not the specific example we'd like to do membership inference on. And we do this a couple of times, say a couple hundred times, so that we can estimate these distributions of what the model loss would look like if the example was a member or not. So now we have these sort of discrete distributions, and the next step, which is kind of maybe doesn't look super important, but is actually very important to get the attack to work well, is that we move from these discrete distributions to continuous distributions by essentially just estimating or sort of fitting Gaussian distributions to these losses. So we just take the hundreds of shadow models we have trained, we measure the mean and standard deviation of the model losses, whether an example was in the training set or not. And then we fit Gaussian distributions to these. And what's nice is that then these probabilities that we need to compute the likelihood ratio test, we can now compute these exactly sort of parametrically by assuming that the loss distributions are actually Gaussian. And so that's then the last step we have to do, is just to estimate these, or to calculate these probabilities given the parameters of the Gaussians that we estimated. And sort of keeping things short, we just find that this attack, which really sort of follows from kind of first principles of what it means to do membership inference, from this idea of doing a statistical test between the membership hypothesis and the non-membership hypothesis, this attack works extremely well. And it doesn't even really matter how you measure the attack success. It turns out that this attack works better than prior attacks on average. But again, this isn't really what we care about. What we really care about is how well the attack works at low false positive rates. And here we find that the attack works still an order of magnitude better than any prior attack, and actually like 3 or 4 orders of magnitude better than some of the simpler membership inference attacks from the literature, like this uniform thresholding attack. So that's great. We now have a membership inference attack that works very well. It turns out that if you look a bit more closely at sort of when this attack works and when it doesn't, you find that the attack essentially works extremely well for data points that are outliers, and it works extremely poorly for data points that are not outliers. And this shouldn't really come as a surprise, right? When we looked earlier at these 2 example images here, in the case of this cat image, it doesn't really seem possible to do membership inference, because whether you train on this image or not, the model's loss is always kind of the same. Like the model is just always going to have very low loss on this image, whether it saw it during training or not. And sort of, it seems like intuitively you just can't do membership inference well for these kind of inliers. And yet what I'm going to show now is a different type of attack, where we can get membership inference to work even for inliers like this cat image here. And so we get these ROC curves that are shown here in bold, where we can get, even for inliers, we can get an attack that works incredibly well, and nearly as well actually as the attack on outlier data.
So Florian, can I ask a question?
Yes.
Okay, so it seems to me that you need to assume that your shadow data set has the same distribution as your training data set, right?
To some extent, yes. I mean, we do some ablations in the paper where we look at cases where the data that the adversary has access to might be from a slightly different distribution, a slightly sort of shifted distribution, and the attack still works, just as not quite as well. It's sort of the closer the adversary's data distribution is to the target distribution, the better the attack will work. Yeah.
Okay.
Cool. Any other questions at this point before I move on to our second attack? Okay, great. Then let me move on and explain how we sort of get membership inference to work for inlier data. So here, actually, we're going to consider a slightly stronger threat model, which is going to make this work. And what we'll consider here is a setting where the adversary can actually interfere with the training of the model. And the way the adversary is going to be able to interfere with the training is through poisoning. So the setting here is that the adversary gets to contribute some of its own data to the training set, and they're going to use this ability to later on leak private information from other users. So you can sort of think of this as an analogy, as sort of the adversary is using their ability to write into the training set to later sort of read off entries from other users. And we show that this sort of combination of attack strategies of data poisoning on one hand and privacy attacks on the other hand is actually incredibly powerful. To give you some intuition for how the attack works and sort of why it works, let's look again at our inlier example here, our cat, where essentially what happens is that there are a bunch of other cats in your cat images in your data distribution. And so essentially whether this specific cat image is in the training set or not, right, just means that the model's loss is really not going to change much. And so that's why membership inference on this particular image is hard. But now what we're going to do with poisoning is we're essentially going to transform this inlier into an outlier so that membership inference becomes easier. The way we're going to do this is by just taking the image we're targeting, this specific cat image, and we're going to poison the model by injecting very similar images that are mislabeled, say as a dog. And so now the model is essentially going to learn that this cat should really be labeled as a dog. And now the presence or absence of our target, which is the correctly labeled image, is going to have a much larger influence on the model, in that if the target image is present in training, the model is sort of going to learn, or is kind of going to memorize that, oh, this specific image should really be labeled as a cat. But then if the image is not there, the model is just going to learn, oh, this is all just this should all be labeled as dog, because it's been sort of poisoned to do this. And this kind of gives you a much better, a much easier way of sort of differentiating between models that were trained on the specific target of this sort of correctly labeled cat image and models that were not trained on it. And so really the strategy that the adversary uses here is to use data poisoning as a way of transforming any input of their choice into an outlier. We find that this attack strategy works extremely well, not just for membership inference, but for many other types of privacy leakage or privacy attacks that you might care about, including attribute inference and data extraction attacks. So what we do here is that the attacker just targets specific examples that they want to attack. And for each example that they want to target, the attack is extremely efficient in that the adversary only has to poison something on the order of like 0.1% of the training set. And for membership, for instance, sorry, for membership inference, for instance, which you can see here on the left, we can get an attack that, depending on how you look at it, is like 1 or 2 orders of magnitude stronger than our prior attack. So if we look at how well the attack works at a fixed false positive rate of say 1 in 1,000, we can increase the true positive rate of the attack by like a factor 8. Another way you might look at this is you might say, I want an attack that has a fixed recall of say 50%. And then in that case, with poisoning, you can reduce the attack's error rate, its false positive rate, by nearly a factor 500. And so you really get an attack that's much, much stronger. And yeah, in the paper, we also look at attribute inference, so the ability of an attacker to infer unknown attributes of certain training examples. And we also look at canary extraction attacks, so where you have, say, a language model where someone's credit card number might appear in the training set, and we show attacks that sort of try to extract the sort of structured pieces of information. And there also we get attacks that are usually 1 to 2 orders of magnitude better than the attack without poisoning. Okay, so these were 2 attacks that I wanted to talk about. So first, sort of our general framework for membership inference attacks through statistical hypothesis testing. And now the second attack that uses data poisoning to also target sort of arbitrary inlier points that were kind of hard to target with our original attack. Now for the rest of the talk, I'll spend a little bit of time talking about defenses. And so here, right, if we want to defend our model, our training procedure against membership leakage, we essentially want to find a way to get these loss distributions to sort of overlap again. We sort of want to make sure that whether we train on a specific example or not, this is going to be hard to infer or to observe for the adversary. And of course, this is maybe going to, I mean, yes, probably going to be unsurprising. The sort of canonical way in which you would do that is, oops, sorry, there's like some very weird rendering of this slide here. But the way you would prevent this is with differential privacy. So differential privacy sort of provably prevents all of the attacks we saw today. Because what differential privacy guarantees, and this is a provable guarantee that holds for any pair of data sets that you consider where the data sets only differ in one example, the output distribution of your training algorithm is going to be roughly the same. And so in particular, because this guarantee holds for any training set, it holds for a training set that has been poisoned, it holds for a training set that contains inliers, that contains outliers, it holds for any target you consider. And so this guarantee essentially means that a membership inference attack is not going to be possible, at least up to some factor epsilon, which is the level of differential privacy. In fact, you can make this connection explicit by showing, this is a nice work by Peter Keruz and his co-authors from a couple of years ago, that shows this explicit connection between the true positive rate and false positive rate of any membership inference attack and the level of differential privacy epsilon. So you can basically show that if you have a certain level epsilon of differential privacy, then this provably bounds the ratio between the true positive rate and false positive rate. And it's also, this is again, I think this goes to show again why the way that we look at these attacks in the low false positive regime, in this kind of log scale, is really what matters. And that what you see here, the quantity that matters here is the ratio of true positive rate to false positive rate. It's not their difference, it's the ratio. And in particular, this means that it's only really at low false positive rates that this ratio can be high. And so what really matters in terms of differential privacy, at least, is how high this ratio can be. And typically this means sort of how high your true positive rate can be at a very low false positive rate. And this is sort of how you get this connection between membership inference attacks and something formal like differential privacy. Now, of course, training models with differential privacy is not easy. Like, people have been trying to do this for years, and it's expensive in terms of training time, but also in particular in terms of just the utility loss if you want a very strong provable bound of privacy. So you might think, well, maybe there's just some simpler defenses out there that we could consider, where we might not get some provable privacy, but where we can still sort of empirically prevent membership inference. I'll talk about two ideas that we studied recently of sort of simple ways that you might try to prevent privacy leakage. The first empirical defense that we looked at is this very simple idea of just removing vulnerable data from your training set. So the way such a defense would work is you train your model, you run a membership inference attack, and you sort of check, well, which points are actually the ones that are vulnerable, which points are your outliers that are easy to infer membership inference on. And then, well, just remove these points from your training set, sort of remove all the outliers and retrain. And hopefully you'll sort of get rid of all the privacy leakage. And what we were quite surprised to find is that this doesn't work. And so we did this experiment and found this phenomenon, which we're calling the onion effect of privacy, which is essentially that once you take the most vulnerable data points in your training set and remove them, there's sort of a new layer of points that become vulnerable. There's a new set of points that become outliers because they're essentially not protected anymore by the previous outliers. Quantitatively, the way this looks here is that here in blue on this plot, you have our original membership inference attack. And then in green here is how well the attack would work if we just removed the 1,000 most vulnerable points. And we just sort of didn't count those when evaluating how well the attack works. And so, of course, the attack's going to work a lot less well if you don't let it target the 1,000 most vulnerable points. So this green line is kind of the best we might hope for. And what we find is that if we actually remove those 1,000 points and retrain the model and then rerun our membership inference attack, instead we get this line here in orange, which is kind of somewhere in between. And so this defense just wasn't as effective as we would have hoped it to be. And by just removing outlier points, you're just sort of making other points become more vulnerable than they were before. So this isn't this was a very, very simple defense idea that we looked at, but that ultimately doesn't quite work as well as one might hope.
Okay, just make sure I understand this. So okay, so the orange line, you remove the data points that you identified as sort of like vulnerable points, right? And then you compute the attack again. But are you now using the remaining data points to compute this ROC curve, or you are using the original one? Because your data set changes, right? Yes.
So in the orange case, so actually in the orange and green case, we're evaluating the attack on all the data points except the originally most vulnerable ones that we've removed.
Okay.
The difference between the two cases is that in the orange case, we actually sort of retrained the model in between.
Okay. Okay.
Yeah. Okay, cool. And then, yeah, so this is the last thing I wanted to mention is a second simple defense idea we recently looked at. And this is just seeing if you could just wait until data that's sort of been memorized by a model ultimately gets forgotten. And so here the setting is slightly different than what we were looking at before. Here we're sort of considering an online training setting where you might sort of continuously train your model on new data. And you might imagine something like this in the case of maybe a model that gets fine-tuned. So you have a model that's originally trained on some data set and then later gets fine-tuned on a different data set. You might wonder, well, what does this do for the privacy of the original data that you pre-trained on? You could also consider deletion requests, so something like the GDPR with the right to be forgotten. If someone comes and says they no longer want their data to be part of your machine learning model, do you sort of have to retrain your model from scratch, or can you sort of just collect more data and just continue training in an online fashion and sort of hope that the model is just going to forget about data after a while? So this is kind of the setting we considered in this work, is to train a model up to some step here marked with this star, and then just remove certain data from the training set and continue training with all the other data, and sort of seeing what this does to the data that was removed. Sort of how fast does the model kind of forget about these inputs? And essentially the way we measure forgetting here is, again, with a membership inference attack. We're sort of looking at how quickly the success rate of the membership inference attack drops once you remove data from your training set. And here again, we find that this is a defense that's somewhat effective. It's maybe not perfect, but we find that models actually forget training data very, very quickly. So here on the left, we have an experiment on ImageNet, where essentially in every epoch, the model is going to, up to epoch 50, the model sees a specific training example, and we sort of measure membership inference precision and accuracy on this specific example. And what you can sort of see is that every time, as soon as the model sees the example, the membership inference accuracy just sort of spikes up, because the model kind of memorizes the example, and then sort of over time, the accuracy sort of drops again. And then at the epoch 50, we just remove this example from the training set and continue training for 10 epochs. And we see that the membership inference goes down quite quickly, nearly to chance. Not quite, but this is we think that this is sort of an interesting phenomenon to consider, that there might just be from the training process itself, from sort of the stochasticity of the training process itself, models might just forget training data quite quickly. We have a similar experiment here on the right on a text and speech data set, where we also have we have some outlier data that we inserted into the training set, and then after 50,000 training steps, we remove this data from the training set, and very, very quickly our ability to sort of extract this information from the trained model goes back nearly to sort of baseline. One way you can also interpret these results is in the context of many modern machine learning models, especially sort of very large language models, are today trained for a single epoch. So you just collect, like hundreds of gigabytes or terabytes of data from the internet, and then you just run one training epoch across this huge data set. And what these results likely mean is that the examples that are seen towards the end of this epoch are much more likely to be memorized by the model than the examples that were seen way at the beginning, because by the time you reach the end of your training set, all the stuff that you sort of that the model memorized early on during training has sort of been forgotten. And sort of this indicates that kind of the order in which data is seen during training might matter quite a bit in terms of what gets memorized and what doesn't. Okay, so let me conclude here with what we talked about today. So the very first thing, I think this kind of the main takeaway from this line of work we initiated on membership inference attacks is that we really shouldn't be measuring the success of these attacks or the sort of the privacy leakage of models in an average case way. This is not the right way to measure privacy, because it doesn't really tell you individually for any individual user whether the attack is actually succeeding at anything. And because we're now sort of saying that we should evaluate these attacks, these membership inference attacks differently, what this actually means for the community is that there's a lot of things that we think we know about membership inference attacks and defenses that we might have to reevaluate. Sort of very, very simple questions like, I don't know, is dropout a reasonable defense against membership inference? If you go and look into the literature, you'll find 3 or 4 papers that one way or another will say something like dropout is a reasonable defense or dropout is not a reasonable defense. But all those papers will have evaluated membership inference in an average case way, using, say, attack accuracy or AUC scores, and they say nothing about how well the attack works at low false positive rates. And so we actually don't know what design decisions in say the training of a machine learning model really influences this sort of worst case leakage. And this, I think, is a space where there's a lot of work, of valuable work to be done to sort of better understand this worst case leakage of machine learning models. Then we saw that with data poisoning, we can really sort of make this worst case setting even stronger, and sort of really any data in the training set can become vulnerable if it's sort of targeted by a poisoning attack. And then finally, we looked at some heuristic sort of empirical defense ideas and sort of used membership inference attacks to evaluate how well these work. And I think this kind of work is also this kind of approach is something I'm hoping that the community will sort of pick up on, and we'll see more attempts of this sort in the future, of sort of researchers proposing empirical sort of heuristic privacy defenses, and then using sort of worst case membership inference attacks as sort of as tests for how well these heuristic defenses work. Yeah, that's it from me. Thanks everyone for listening. I'm very happy to take any questions.
Okay, so yeah, thanks, Florian. Okay. So, okay, great. Okay, we do already have questions, but maybe, okay. So, Mingxue, do you want to unmute yourself, or should I actually read out for you?
I can see myself. Yeah.
Okay.
Great, thanks for your talk. I have 2 questions. The first is about the white box attacks. It is not very common compared with black box attacks. So could I ask for the opinion about the application scenario and also the performance of white box attacks compared with black box attacks? Yeah.
Yeah, it's a very good question. So first of all, whether you consider white box attacks as part of your threat model or not is so here, I guess, by a white box attack in the case of membership inference, we really mean like, can you leak membership inference better if the adversary can see the parameters of the trained model and not just the loss or the confidence. So in some settings, in some attack settings, an adversary, of course, might have access to the model in a white box. And on top of that, if you just consider membership inference as sort of a way of bounding the leakage of your model, then I would say that you should sort of give the adversary as much power as you can. And so there, considering the white box setting makes a lot of sense, in my opinion. It turns out that when we look at attacks in this sort of low false positive regime, we don't know how to make use of white box access to make the attacks stronger. So this is this is one of these things that I mean here when I say that we sort of have to reevaluate what we know about membership inference attacks, is that there have been some papers in the past that looked at white box membership inference and sort of suggested that those attacks could be slightly stronger than black box ones, but only when evaluated on average. Sort of the attacks might get sort of slightly higher AUC or slightly better accuracy. When we look at low false positive rates, we have no evidence that white box access helps. And so I think this is an amazing question to study, is like, can you actually show how to leverage white box access to a model to get stronger sort of worst case membership inference? This would be very, very cool. For your second question about sort of the efficiency of training shadow models, this is a bit of one of the downsides of our attack to run it, is that you need to train sort of a bunch of shadow models. In our paper, we do some experiments on this, and we find that you don't actually need that many shadow models for the attack to work extremely well. So even if you have like a dozen models or something, the attack already works quite well. But still, this can be quite prohibitive. And here again, whether you consider this an acceptable cost for an attack depends a little bit on your on sort of why you study membership inference. For an attack on an actual model, like say when we try to extract data from GPT-2, we can't go and retrain GPT-2 a dozen times. Even retraining it once is kind of out of scope in a way for an academic budget, at least. But if what we consider is really sort of our ability to evaluate the worst case leakage, then I think it's important to sort of consider attacks that are quite overpowered in some sense, so that we don't underestimate how much privacy leakage there can be in these models.
Okay, thank you. Thank you so much.
Okay, we do have other questions in the chat, but maybe that we can also let people who raise hand to ask questions. So maybe Helena.
Yes, hello. Thank you very much for your talk. I was wondering if you could talk a little bit about privacy attacks for generative models, because here you mostly focused on classification.
Yeah, that's a very good question. So the language models that I mentioned early on in the talk, so those you can think of those as generative models, and there with language models we now have plenty of evidence from the past few years. It's not things I talked about here specifically, but we have a bunch of work on sort of showing that language models really just emit training data, and typically a lot of it. With other types of generative models, like with say models trained on images, it's a bit harder to evaluate leakage, because a generative model might sort of output an image that is not sort of exactly the same as a training image, like on a pixel level, but might still let you infer things about training data. And so this is just typically not very easy to evaluate, especially if you look at some of the recent large-scale generative models people have been training. So things like Stable Diffusion or DALL-E or models like this. I'm sure there's some amount of data memorization that happens in there, because these models are extremely good at generating relatively rare things they've seen in their training sets, and their training sets also fairly poorly curated. And so it wouldn't surprise me that there are specific examples, maybe or specific images that just appear many times in the training set, for example, and that the model would have just memorized and can regenerate sort of exactly.
So as a follow-up, let's say, what are your thoughts on training again, for example, with differential privacy? Do you think that would fix, if we're talking about images, would that fix the problem, or would you just get blurry images all the time?
So from a formal perspective, it does fix the problem. I guess the two caveats could be, one, if you really have this issue that your training set sort of contains many duplicates of certain images, which is actually very often the case, then differential privacy sort of formally doesn't really save you, because if something appears just too many times in the training set, then the model might just have to memorize it in order to get a low training loss. But if you have a data set that's sort of properly deduplicated and you train with differential privacy, then you kind of provably prevent these kind of attacks. You provably prevent an adversary from being able to extract individual training examples. Whether you still end up with a model that's useful, that's kind of another question. And in particular for generative models, it's been very hard to train models that get sort of a reasonable level of privacy while still being somewhat useful. So this is still, I think, a bit of an open question of how to train these generative models in a privacy preserving fashion. Yeah.
Thank you very much.
Okay, so maybe let's just ask for the final question. Okay, so Xiaoxi, so you want to speak yourself or?
Hi, I'm a fourth-year PhD student working on EEG transfer learning of brainwave decoding across data centers. So this very sensitive data of medical records. So may I ask, what's the prerequisites of membership attack or model inversion attack? Do they require knowing the parameters of the feature extract network or gradients? So can we hide or encrypt those parameters to prevent from the attackers? Thank you.
Yeah, that's a great question. I guess this comes back to the earlier question about sort of considering a white box or a black box threat model. So specifically the attacks we look at here, all they require is the ability to query the model and get back essentially the model's confidence. So it's really kind of a fairly minimal amount of information you need. We had some prior work a couple of years ago where we looked at membership inference attacks in a setting where all you get from the model is a class label. So sort of really the minimal amount of information you could expect from sort of an input-output interaction with machine learning model. And we showed that even there you could get membership inference attacks to work if you can query the model many times. So in practice, I would say if you're really concerned about these attacks on a real data set, it depends a lot on how much interaction with the model an attacker could have, and how much information each of these interactions leak. So if every time the attacker queries the model, they only get back sort of a class label and they only get to query the model like maybe once or twice, then I think you're probably good just because you're minimizing the amount of information that the attacker is given so much. But if you're in a setting where an attacker can sort of freely interact with a model and get back sort of quite fine-grained confidence scores every time, then you're getting much closer to the sort of worst case leakage that our attacks estimate. Yeah,
I see. So better we hide both of the feature extractor and the classification layer to protect the privacy.
Yeah, in a sense, sort of the more you hide about the model, the better. I guess at some point, ultimately the question is like, whatever predictions your model makes is going to be used for something, and so there's always going to be some observable outcome, of course. Understood. And so there might still be some leakage from this. Yeah.
Thank you very much.
Okay, maybe in the interest of time, we can just allow the final question. If Javier, your question will be quick.
Hello. Yes, thank you very much. So thank you very much, Florian, for your interesting talk. So I'm a PhD student here at Imperial College, and I'm working on poison attack. So I'm wondering, like, for the poison attack that you mentioned, so you basically flip the label of the target point. So I was wondering if that in practice could be easily detected, and if that actually will depend on how far. So the privacy leakage will depend on how far the poison point is from the original distribution. Thank you.
Yeah. So to be honest, when we looked at these attacks, we made essentially no effort to have the attacks be sort of hard to detect. This was for two reasons. One being that we just wanted to see sort of how far we could push this idea, or sort of whether it was even feasible. And the second is that with modern data sets, it's actually, I think it's very, very hard to detect any type of poisoning attack, because you have the training sets that are typically used today have billions of examples. The data is extremely noisy, and so you will actually have many mislabeled examples in there anyhow. And the general trend today seems to be to just let it be, and kind of the more data you have, even if the data happens to be quite noisy, that's still a good thing for getting models to work. And I think because of this, poisoning attacks on sort of large scale machine learning today is probably very, very easy, and I think we're actually going to start seeing more of these attacks in practice as well, because it just seems like they should be extremely easy to run. You could probably make these attacks more stealthy. Like there is some literature on poisoning attacks that are what's called clean label, where you essentially, instead of changing the label of the image, you change the image itself, sort of using techniques from adversarial examples to kind of get the same effect as mislabeling. We didn't really try this in our work. I feel like it probably should work. It might make the attack slightly less effective. But yeah, we didn't really consider making this attack stealthy.
Yeah. My guess is that in that case, probably the privacy leakage depends. If you don't fully label, it actually depends on the kind of the norm or the perturbation that you have, probably.
Yeah. Which again sort of comes down to a question like, is there actually going to be anything in place to detect these type of attacks? And if we sort of look at machine learning pipelines of today, like no one seems to be running any kind of mechanism to detect tampered training data. We don't really know of a good way of doing this, to be honest.
Right. Thank you very much.
Yeah, sure.
Okay, great. So yeah, thanks again, Florian, for the very interesting talk and also answering the questions from the audience. So this concludes today's talk. So thanks everyone for joining.
Yeah, thanks everyone. This was really fun.
Thank you very much.